to actually quantize the theory. We've already discussed the Hamiltonian formalism. We found the conjugate momenta. And so all that's left to do is to impose some commutation relations. So as is familiar to you from quantum mechanics, we have some set of generalized position, Q, A, and their associated conjugate momenta, P, B. Then the standard procedure is to impose the commutation relation that QA, commutator of QA with PB is I delta AB. So remember, we're using natural units where H bar and also C are 1. And similarly, we want to impose the commutation relations that QA with QB is 0, as is PA with PB. Yeah. So we want to do essentially the same thing in QFT. So we'll start out in the Schrodinger picture. We'll discuss the Heisenberg picture later. But remember, the analog of the generalized position are fields. And we computed the conjugate momenta last time. So we're going to impose the commutation relation that commutator of phi with pi is I delta. This time, a Dirac delta instead of Kronecker delta. That's just because our position is continuous instead of discrete number of generalized coordinates. And likewise, we want to impose the commutation relations that the field and its momenta commute with themselves. All right, so that's it. So we've quantized the theory. We'll see what this means later. And at the end of yesterday's lecture, we spent a while solving the Klein-Gordon equation and writing the solution in a as Lorentz invariant manner as we could. And so if we set t equal to 0 in our result from last time, then what we have is this expression. And so if we're promoting the fields to operators, we need to promote something on the right-hand side of this equation to operators. And the natural choice is to promote the functions a and a star to operators, creation and annihilation operators, a and a dagger. So we promote this to a annihilation operator, AK, and this to a creation operator, AK dagger. Then this equation makes sense as an operator equation.
In those commutation relations, the argument is the 3-vector, spatial 3-vector, or 4-vector?
This is the 3-vector. So we're working in the Schrodinger picture. So our operators are time independent. We'll talk about the Heisenberg picture later. Yes?
In the integral there? Are those exponentials supposed to be 3 vectors?
These are the 3 vectors. Again, we're working in the Schrodinger picture. So you can, say, choose a time and say t equals 0. So so if we're in the Schrodinger picture, all of our operators has to be time independent. So we don't want any time dependence in this equation. In the middle of the lecture, we'll discuss what happens in the Heisenberg picture. But it's basically what you'd expect, that time dependence will reappear here. OK. Any other questions on that? OK, so these commutation relations imply a set of commutation relations for the creation and annihilation operators. And the results are that commutator of AK with AK dagger is 2 pi cubed 2 EK delta K minus P. And the creation operators and annihilation operators commute among themselves. So you will show these results in tutorial. All the assumptions you need are just these equations, and this follows. So you'll derive this for yourself in tutorial. Furthermore, you'll also derive the Hamiltonian operator, which follows from the classical Hamiltonian that we computed last time, as well as this equation here. And again, you'll work this out in tutorial. I'll just state the result. So all of these results you'll derive in tutorial. So this E cancels, but I'm just leaving it there just to leave our Lorentz invariant measure intact. And so when we look at this Hamiltonian, it looks fairly familiar. So if we just ignore the measure for now, it's just 1/2 EK times this combination of creation and annihilation operators, which should look familiar to you. This is just the Hamiltonian for a harmonic oscillator. So what we have here is the Hamiltonian for infinitely many decoupled harmonic oscillators. There's no terms here that mix creation or annihilation operators with different momenta. So what we have here is just infinitely many decoupled oscillators, and the Hamiltonian is just the integral over all possible momenta for those oscillators. And so that's a useful picture to have in mind. OK. So these are the most important Schrodinger picture operators in the free Klein-Gordon theory. So the natural question to ask next are, what are the states in this theory? So the simplest state is the vacuum. I will denote as 0. And the vacuum has the property that it's annihilated by all of the annihilation operators. And we can also choose a normalization. Let's choose the normalization that the inner product of the vacuum itself is 1. Okay. So this is the vacuum. And one question we can ask is, what is the energy of the vacuum? So if we act with the Hamiltonian on the vacuum state, vacuum state is a eigenstate. So we'll just get back the energy of the vacuum. And using this Hamiltonian operator that you'll derive for yourself in tutorial, you can write this as a half that's the Lorentz invariant measure K dagger. The other term is just 0 by this property of the vacuum. With any annihilation operator in the vacuum, we get 0. And so we can then use the commutation relation to switch AK dagger and AK. The term with AK against acting on the vacuum just gives 0 again. And so we're left with 1/2 integral d3k ek times delta of k minus k acting on 0. So the commutation relation gives us a factor that cancels out the denominator here. And this expression is horribly divergent. Maybe a bit concerned. Our very first calculation in quantum field theory gave us infinity. Actually, we shouldn't be so surprised by this. And it's not as bad as we think. So what's going on here?
Sorry, what happened to the EK on the bottom of the factor?
So in the commutation relations, there is a factor of 2 EK.
Yeah, sorry.
It's all right. Okay, so what's going on here? There's actually 2 different infinities. And so let's try to understand them one at a time. And the first infinity is what's known as an IR divergence. So IR here stands for infrared, and it means it has to do with large length scales or small energy scales. And we can understand this. We can regulate this divergence by putting the theory in a box of size L. With periodic boundary conditions. Say. And so we can try to understand this first divergent factor, which is delta of 0. So delta of k minus k up there, as follows. So we can write this delta function in a slightly unusual way. So we can write as the limit L goes to infinity, the integral from minus L over 2 to L over 2 to the I x dot p evaluated at p equals 0. So this integral, if we forget about this, setting p equal to 0, would just give us delta of p. When we set p equal to 0, we get or times 2 pi cubed. We would just get delta of p, and then if we set p to 0, we get delta of 0. But we can also write this right-hand side, if we set p to equal to 0 first, as the limit L goes to infinity of the integral from minus L over 2 to L over 2 d cubed x, which is just the volume of space. So we get a divergent ground state energy. Well, one reason we get a divergent ground state energy is because the volume of Minkowski space is infinite. So if we have an infinite spatial volume, of course we get an infinite energy, unless the energy density is 0. So maybe a better question to ask is not what is the energy of the ground state, but what's the energy density of the ground state. So let's try to compute that. Okay. So the energy density is E naught over V. And we'll interpret this 2 pi cubed delta of 0 as V. And so if we do that, what we get is this integral which still diverges. So this is just the sum of the ground state energy of each of the harmonic oscillators. So this is what's known as a UV divergence. And so maybe it's disconcerting to you, but we shouldn't worry too much about it. So there's several reasons for that. So first of all, this divergence really comes from the high energy behavior of our theory. So our theory is only good up to some finite high energy scale, say the Planck scale, then this divergence would disappear. So one reason, or one explanation for why this isn't really a problem is because we said we trusted our theory up to arbitrarily high energy. And any realistic theory, the Free-Collin-Gordon theory is not a realistic theory, but any realistic theory that we want to use to explain some physics is usually going to have some range of validity. We don't know what the arbitrarily high energy physics are. So if we get a problem by extrapolating our theory up to arbitrarily high energies and get a problem, maybe that's because we shouldn't have extrapolated our theory up to arbitrarily high energies. So that's one way we can get around this problem. A second answer for why this isn't a serious issue is that so we're doing non-gravitational physics here. And so what's usually relevant for non-gravitational physics are energy differences, not absolute energy scales, values of the energy. If the energy of the ground state is divergent, but differences in energy are finite, then again, we shouldn't be so concerned about that. And so we'll come back to some related issues when we talk about renormalization, particularly in QFT2, about UV divergences. But for now, for most of this course, we're just going to ignore this issue. by normal ordering. And so this normal ordering just means putting all of the annihilation operators to the right. And so the normal ordered Hamiltonian then just becomes this. So we just take the Hamiltonian on the top board and by hand, without using the commutation relations, just move all the annihilation operators to the right. And
Sorry, so what do we, annihilation to the right?
yes, so this means annihilation to the right. And many of the operators we'll consider will have similar issues, and our solution for now is just going to be to normal order everything. And we'll discuss this issue a bit more in tutorial today. So more on that later. OK, so that's first and simplest state. And we already saw several interesting effects that were new to quantum field theory. So let's construct the other states.
So in this normal ordering, we are ensuring that our theory, the energy of the vacuum is going to be zero.
Yes, this if we act with the normal ordered Hamiltonian on the vacuum state, we'll just get 0 because there's an annihilation
And
operator.
is this physically real? I mean, the energy of the vacuum is something real. When we have Casimir, and it's not zero.
So we'll discuss the Casimir effect in tutorial today. So it's about we'll come back to. But yes, so for the real world has gravity, and so of course the ground state energy is extremely important gravitationally. So this is related to the cosmological constant problem. It's really an open problem. So
But Casimir doesn't have to do anything with gravity. It's just a fraction because of the electromagnetic interaction.
yes. So again, I want to defer that discussion into tutorial, but please do ask me again about the Casimir. Well, we will study the Casimir effect in tutorial today. So I'd like to defer that discussion until tutorial until you'll see the problem. But please do ask me again during tutorial.
So we use the normal ordered Hamiltonian only in the vacuum, or like in general? Like,
In general, so we're always going to
and that
work
doesn't-
with a normal
that
order.
doesn't massively screw up this theory.
No.
Because that's kind of surprising, because the whole point of QM is that these things don't like operators don't commute. Right? And now you're just saying like, we're kind of like not going to not use the commutation relation. And work with the
Well,
object,
so if we do it for everything, then really we're just basically you can think of it as subtracting an infinite constant from this operator. So that's yeah. Okay, so that is the vacuum state. So the other states have particles in them. And so let's discuss those now. So we can construct other states by acting with the creation operators on the vacuum. And the simplest such states are the one-particle states, where we act with precisely one creation operator. On the vacuum state. And so you'll learn more about these in tutorial. So some of the results I'm just going to state are results that you will derive in tutorial. But I just want to briefly discuss them. And so I'll introduce this other notation, a slightly shorthand notation for the one particle states. So denote the state with momentum k, the one particle state with momentum k, just using this notation. It means the same thing as acting with the creation operator with momentum k on the vacuum state. And so these states have energy Ek and momentum K, just like you'd expect. So if it's a one particle state, you'd expect it has this energy and this momentum if it's a particle with mass m. So you'll show this in tutorial. Again, these results assume that you're using the normal ordered operators. Okay. So one important property of the one particle states is that they are not unit normalized. So we can compute the inner product of P with K. And that, just by definition, is AP AK dagger. Which, using our commutation relations, just gives us this. So they're not unit normalized. This normalization, for most purposes, turns out to be more useful. So this is a Lorentz invariant combination of the energy and this delta function. So the argument is basically the same as the argument that the measure we discussed at the end of the Lorentz invariant measure we discussed at the end of yesterday's lecture is Lorentz invariant. So the same logic implies that this combination of energy and the delta function and momentum is Lorentz invariant. And this sort of normalization means that our states are Lorentz covariant. And it's just much more convenient. Word of caution, though, is not all authors use some of the references that I listed on the wiki. Other authors use different choice of normalization. So be careful. Okay, so those are the one particle states. And we can just repeat this process by acting with more.
The inner product itself is a scalar? Is a Lorentz scalar?
Lorentz scalar, yes.
So the Ek is not part of the four vector. So
Yes.
the delta 3 function is not.
That's right. They combine. This product is Lorentz invariant. So we can construct n particle states just by acting with n creation operators on the vacuum. And we will denote the n particle states as K1 up through Kn, where we just enumerate the momenta of each of the particles. And so that this is just a shorthand notation for A dagger K1 up through A dagger Kn, acting in the vacuum. And since these commute, these creation operators commute, that tells us that the Klein-Gordon particles are bosons. So we can also write down a number operator, which is just integral d3k, 2 pi cubed, 2dk, ak dagger, ak. which is just like the normal ordered Hamiltonian without the extra factor of energy. And so if we act with this number operator on an n-particle state, we'll find that the n-particle state is an eigenstate, and it has eigenvalue n. So this combination will just count the number of creation operators there. And from the form, because the form of the number operator is so similar to the form of our Hamiltonian, it should come as no surprise that the number operator and the Hamiltonian commute. So this implies that particle numbers conserve. And so one of the goals of that I stated at the beginning of yesterday's lecture was for QFT was to be able to describe processes in which particle numbers not conserve. So here we've written down a theory where quantum field theory, but that conserves particle number. So the reason for that is just because our theory is so simple. We have no interactions. This is known as a free theory. And basically all of the other theories we will discuss throughout this course, well, the exception of some other free theories that Tibor will tell you about, will have interactions and will not conserve particle number. So this is, in general, only true in free theories.
Yeah, I mean, if we put the normal Hamiltonian, not the normal other Hamiltonian, that would still be true.
So we would have an extra term. The extra term is basically just a constant, so it should still be true. And so these are, well, this is the basis for all the states. And the total state space is what's known as a Fock space. So it's the direct sum of all of the n-particle Hilbert spaces, which we can write like this. So those are the states of the free Klein-Gordon theory. So, so far everything I've discussed has been in the Schrodinger picture. It will sometimes be useful to instead work in the Heisenberg picture. And the Heisenberg picture, the operators become time dependent. And time dependence operators can be found from the Schrodinger picture operators in the usual way. So we have a Schrodinger picture operator O. We can write the Heisenberg picture operator, which I'll denote as O of t, in just the usual way. And it's worth writing down explicitly what the time dependence of some of the most important operators in our theory are. So the annihilation operator in the Heisenberg picture can be found from the Schrodinger picture Heisenberg operator, which, using the BCH formula that e to the a, b, e to the minus a is b plus a, b plus a half a, b, so on. And this commutation relation between the Hamiltonian and the annihilation operator, we can get the time, how the Heisenberg picture annihilation operator is related to the Schrodinger picture. And we just get this factor minus IUPT AP. And similarly, the creation operator Heisenberg picture is just related to the Schrodinger picture operator, just with the opposite sign in the exponent. And so, using these relations and our expression for the Schrodinger picture field operator, we can get the Heisenberg picture field operator, which is basically just what you'd expect. And so, again, this is basically our result from the end of yesterday's lecture. So this is nice and Lorentz invariant. Whereas the Schrodinger picture things look less Lorentz invariant. But there's still some Lorentz invariance is not manifest even if we work in the Schrodinger picture. And that's because even though the field operator, again, looks Lorentz invariant, the commutation relations that we wrote down in the Schrodinger picture, if we write them down in the Heisenberg picture, they only take the simple form that I wrote down before if we set the time argument of the field operators to be the same. So if we impose, in other words, if we impose equal time commutation relations. So at equal times, the field operators in the Heisenberg picture obey the same commutation relations as in the Schrodinger picture. But these expressions would look much messier if we tried to write this down for general time arguments of the two fields. Okay. All right, so not obvious that everything is going to work out to be Lorentz invariant, because this choice of time keeps reappearing. One property we particularly care about is that our theory is causal. And so causality for us means that we require that commutator of two operators should vanish if x and y are space-like separated. So the reason we want to impose this is to ensure that a measurement of an operator at x cannot influence the result of a measurement of an operator at y if x and y are space-like separated, and therefore not causally connected. So we won't show this for all operators, but one of the simplest, and most important operators in our theory are the field operators, phi. And in a few minutes, we will compute their commutator. Let me just give it a name. And I just want to state the result and make a few comments about it before we go ahead and do most of the commutation of it. So the result will be So just want to point out a few things about this result. So first of all, it's Lorentz invariant. So each piece of this expression is Lorentz invariant. We've got Lorentz invariant products in the exponential are a Lorentz invariant measure. So that's good. So delta is Lorentz invariant. Second, we notice that it is an operator. Sorry, number, not an operator. This is only true in the free theory. If we tried to compute the same commutator in an interacting theory, in general, we'd get an operator on the right-hand side as well. And the fact that it's a number, not an operator, will simplify some of our calculations a little bit. Furthermore, it vanishes for space-like separation, which is essential. Otherwise, you have a non-causal theory. And so why is this? So to see this, let's look at our expression over here. So if x and y are space-like separated, we can choose a frame where x naught is equal to y naught. So if x naught is equal to y naught, then the 0th component of the momentum doesn't contribute. And so then we have here then just two exponential terms that are the same except for the sign and the exponent. And we can take the 3 momentum to minus the 3 momentum like we did several times yesterday. The measures invariance, and then we can just in one term, and then we can just flip the sign and the exponent in one term, and the two terms cancel. Was that too fast? Does that make sense? All right, so the last property it has is that it's non-zero for time-like separations. That argument won't work, and in general, there's no reason to expect this to be 0 if x and y are time-like separated. Okay. Okay, so where does this result come from? So before we compute commutator, we can ask a slightly simpler question. So one question we can ask is, what is the amplitude for a particle to propagate from x to y? Or from y to x, or I guess. So this is the amplitude for a particle to propagate from y to x. And why is that? So, very good question. That is because we're going to interpret this as a state with a particle at y. And so, since this is a real field, this is a particle at x. So why do we have this interpretation? So remember, the field contains both a creation and annihilation operator. So we act with it on the vacuum state. We'll get a one-particle state, and it looks kind of like a Fourier transform. So I'm not going to be more precise about that, but it's just a useful interpretation of this state. It is a one-particle state. That's certainly true, and we'll think of it as a state where the particle is localized at y. Okay. So we can compute this using our expression for the field operator in terms of the creation and annihilation operators. So just have two integrals. And so there are 4 terms in the expression, but 3 of them vanish because they'll either contain a annihilation operator acting on the ket vacuum or a creation operator acting from the right on the bra vacuum. So we're only left with 1 term, and that's this term, where we have a p and a k dagger. And then we can use the commutation relations to switch the order of a p and a k dagger. And if we do that, we'll get a delta p minus k, together with a factor that will cancel the denominator in one of the integrals. And then we can do the integral to set p equal to k. So what we're left with is this expression. Okay. And so this is just 1 term in our results for the commutator. And we'd get the other term if we just switched x and y with the minus sign. So we've derived the expectation value of delta. So what we've shown already is that this is equal to 0 delta x minus y, 0. So we've almost shown this result. So the way we could show this result, I'm not going to go through the algebra, it's just a bit messier than what I want to do, is we canceled off 3 of the terms using the vacuum states. Those terms will also cancel. They would also cancel just between the 2 terms in the commutator. So that's why this is just a number, and delta is equal to the expectation of delta. I encourage you to check that if you don't believe me.
When we performed the 3 integration over the delta function and we set p equal, and we set the energies equal.
Yes.
Is that because the energy depends on the square root of p squared plus m squared?
Yes. So every time it's a very good question. So every time I write an exponential that has a floor vector in the exponent, we're always integrating, or we're always so far integrating over just the spatial components.
Yeah.
Should always interpret expressions like this with an implicit. So we interpret something like e to the I p dot x. So this should be, in my notation, this is equal to e to the I p dot x evaluated at p naught equals ek, which is equal to the square root of k squared plus m squared. So anytime we have a integral d3 x. That's what I meant. I just have not been writing this, but this is implicit in many equations.
Thank you.
Okay. So we've now computed the amplitude for a particle to propagate from y to x. So we can ask a similar question like we asked before. Before we wanted to demand that the commutator vanished outside the light cone. So one question you might wonder about is, does the propagator, does the amplitude, is there a non-zero amplitude for a particle to propagate from some spacetime point y to another spacetime point x outside of its light cone? So let's look at that. So let's suppose that x and y are spacelike. So then we can choose a frame, say x naught minus y naught is 0, and x minus y is r. Then dx minus y is integral d3 p 2 pi cubed to ep dr. And this integral can, well, so first of all, if we just look at it, there's no obvious reason why it vanishes. In fact, it doesn't. It can be evaluated exactly in terms of special functions. I'm not going to go through that, but the result is that it's proportional to a modified Bessel function of the second kind. And this has the asymptotic behavior as r goes to infinity, that it goes like m to the 3/2 4 pi squared r to the 3/2 squared pi over 2 e to the minus mr as r goes to infinity. So it does decrease exponentially fast, but it's non-zero. Is this concerning?
M to the, M to the,
Here, m to the 3/2.
okay.
Okay. So let's draw a picture of what's going on here. So we've got some point x, or some point y, some point x. That's space-like separated. And we've just found that there is a non-zero amplitude for a particle to propagate from y to x. So you might, well, we've shown that it's causal, but how does that result if there's a non-zero result occur if there's a non-zero amplitude for a particle to propagate from y to x? So if there's non-zero amplitude to propagate from y to x, there should also be a non-zero amplitude to propagate from x to y. And so these two amplitudes will cancel each other. And so that's the reason why this commutator vanishes. So this commutator is dx minus y minus dy minus x, which is 0. So the amplitude, both of these amplitudes are non-zero, but they cancel. So we're dealing with a real scalar field. So there's no distinction here between particles and antiparticles, or if you like, the particle is the same as the antiparticle. But if we were dealing with, say, a complex scalar field, which we really briefly discussed yesterday, we would have distinct particles and antiparticles. And in that case, the cancellation in these amplitudes would be between a particle propagating from y to x and a antiparticle propagating from y to x.
So can you explain why we have to subtract them to cancel them?
So if we're computing the commutator,
Why do we compute the commutator?
well, we want the commutator to be 0 to ensure that our theory is causal. So to ensure that a measurement at y will not affect a measurement at x.
Okay. Yeah.
So that's the most important property we care about. And so these, so what I've implicitly used here is that this commutator is equal to the expectation value of this commutator, because it's just a number.
Thank you.
So we see that the commutator is 0, but the process itself of a particle propagating from one.
Right.
Is that actually happening?
That's what our theory tells us, but there's no way to measure it because.
Okay, so maybe it's not. There's
Yeah.
no way to measure it, but still inside the theory is possible.
It's still inside the theory, yes. There is a non-zero amplitude to propagate outside of the light cone, which is unexpected.
But in mean values, we don't see that. That's the idea.
That's the idea.
Okay.
Okay. So that's what's happening outside the light cone. So what is going on inside the light cone? So inside the light cone, so let me write down some expressions that will not be obvious at first, but I'll explain them after I've written them down, and it'll be easier to understand from the bottom up what's going on here. So first of all, this is just our result. For commutator. write two lines that I'll explain in a minute. Okay, so what we're trying to do, and it shouldn't be obvious why yet, but by the end of the lecture, hopefully it will be, we're trying to write the commutator as a contour integral. And here, this contour CR is the following contour. So the integrand here has two poles in the complex P0 plane. So we can see that if we write this as P0 squared minus EP squared. So it's got poles on the real axis at plus and minus EP. So for this integral to make sense, we need to avoid these poles. So we're going to integrate along the real line, except for infinitesimal excursions into the positive imaginary, the upper half plane. Okay. So for some reason that I'll explain later, we're trying to write this as a contour integral. And okay, so these equations are probably somewhat mystifying, but let's try to explain them from the bottom up. It's easier to see it that way. So to go from the third line to the second line, assuming x naught is greater than y naught, so that's what this x naught greater than y naught under the equal sign means this equation, this second line is equal to the third line only if x naught is greater than y naught. So if x naught is greater than y naught, then we should close the contour in the lower half plane. If x naught is greater than y naught, we know that p naught is positive, so then we want to, or sorry, we're integrating over p naught, so we want to have we want a decaying exponential here. So if Okay. It's not as,
Yeah, it's okay.
that's right. That's right. Yeah. We have two minus signs. Minus sign from the imaginary part. Minus sign here, and then or 3 minus signs. So yeah, it's a decaying exponential. Okay. So if we close, so we should close the contour in the lower half plane. We don't want to get any contribution from this semicircle. And then we enclose the 2 poles at EP and minus EP. And so that's where the second line comes from. So if we do the contour integration, we get 2 contributions. One from the pole at EP, and one from the pole at minus EP. And these are just the residues here and here. And then to go from the second line back to the first line, what we can do is, so the first term is, it's clear, this is just, the first term is the first term here. To get the second term, what we need to do is take P to the spatial part of P to minus the spatial part of P. Because here we're evaluating P naught at minus EP. So if we want to write this just as a 4-vector with our usual implicit notation that P naught is equal to EP, we should flip the sign of the spatial part of P. And that doesn't change the measure, as we've seen many times. So that's why the second line is equal to the first line. OK. So that tells us, well, do a little bit more. So this is equal to this if x naught is greater than y naught. What if x naught is less than y naught? If x naught is less than y naught, we should close the contour in the upper half plane. And then we get 0. The last line is equal to 0 if x naught is less than y naught. And so that tells us then that the last line is equal to something I'll call delta R, which is just a Heaviside function of x naught minus y naught times the expectation value of the commutator. And this is just equal to the integral this contour d4p over 2 pi to the 4th I over p squared minus m squared. And so this is the first time we've ever written, well, except for when we showed that the Lorentz invariant measure was Lorentz invariant. But other than that, this is the first time we've ever written down a 4-dimensional momentum integral. So in this expression, we're not imposing that P naught is equal to EP. Okay, so what does the R stand for? The R stands for retarded. So this is a Green's function for the Klein-Gordon operator. And let me show you that. So to see that this is a Green's function, we can just act with the Klein-Gordon operator. D squared plus m squared on this function. And we get the derivative just brings down a factor of minus p squared and the m squared e to the I p dot x minus y. This cancels the 1 over p squared minus m squared, giving us just a factor of minus I. And this is an integral we all know how to do. Just gives us minus I delta x minus y. So that's what we'd expect. It's a Green's function. And so it's a retarded Green's function because we can use it to solve the Klein-Gordon equation. When we want to impose boundary conditions in the past and evolve forward. So we can use it to solve this equation, where this is a classical source. With boundary conditions in the past. Similarly, we could define an advanced Green's function, which would be just the same. Except we would switch the sign of the argument of the Heaviside function. And the expression for the advanced Green function would be exactly the same as for the retarded Green's function, except we would choose a different contour. This is the advanced contour. And you notice when we showed that the retarded Green's function was a Green's function, we didn't use the fact that the retarded Green's function went around the poles in a certain way. So any way we went around the poles would be fine. All we care about here is that this contour is basically infinitesimally close to the real line. There's no poles in this integrand. So the advanced Green's function is also a Green's function. And we could use this to impose boundary conditions in the future. So these are the two most, if you're interested in classical physics, these would probably be the most interesting and useful Green's functions. However, we want to do quantum field theory. And neither of these Green's functions will be particularly interesting to us.
John, can I just ask, when we're doing these contours, do we want the poles to be inside or outside the contour?
Well, so if they're outside the contour, we'll just get 0. If they're inside the contour, we'll pick up a contribution from that pole. But, well, it depends on what question you're asking. So,
But like, is there not just like, does the integral not have an answer that is correct?
this, so this integral depends on the parameters x and y. So for a given value of x and y, this integral has a definite value. But the functional form of this integral changes depending on what x and y are.
So that's not, like, we're not taking the limit of that integral as it goes to the real axis or anything.
Well, yeah, I mean, I like to think about these as being just infinitesimally away from just avoiding the poles by an infinitesimal amount. But it doesn't really matter doing this line.
Because if they're avoiding them infinitesimally, then why should we choose one direction for them to avoid them infinitesimally?
Oh, well, it will change our answer. So the retarded Green's function, we're avoiding them in one way, and we get one expression. So we'll get, for a particular value of x and y, we could compute the retarded Green's function, and we'll get a different answer from what we would get if we chose the same value of x and y and computed the advanced Green's function.
Yeah. Okay.
So this choice does matter. It affects our final answer.
Okay.
Different choices are interesting for different reasons. So if we were doing classical physics, these are the two most interesting choices for avoiding the contours. So we might be interested in solving initial condition or final condition problems. But that's not what we're interested in doing. What we're interested in is quantum field theory. And a third choice of contour is going to be very relevant for us. Okay. So and this Green's function is known as the Feynman propagator, and it's defined as follows. So I define it to be the propagator from y to x if x occurs after y, and the propagator from x to y if y occurs after x. Or the amplitude to propagate from x to y. And so this expression is rather lengthy, and we will see it over and over again. So it's useful to introduce a shorthand notation. This is the definition. And here, this T is what's known as the time ordering symbol. And it means put the latest operator to the left. So you have a time ordering symbol, just by hand, you time order whatever operators follow it, putting the latest one to the left. Again, not using the commutation relations. And we can write this as a contour integral. It's more common instead to write it like this. Where this I epsilon you can just think of as a mnemonic for the following contour. I'll call it CF. And Feynman contour in the complex P0 plane goes around the two poles at plus and minus EP in the following way. So first it goes below the pole at minus EP, and then it goes above the pole at plus EP. And so this contour is just a mnemonic to sort of take the contour along the real line and rotate it by an infinitesimal amount around the poles. And so these two contours are the same if this is just an infinitesimal rotation.
Where do we close the contour?
So again, where we close the contour will depend on x and y. And so this, it again is a Green's function for the Klein-Gordon operator. It corresponds to only allowing positive frequency modes in the future and negative frequency modes in the past. So it's less useful in classical physics than the retarded and advanced propagators. But it's extremely important for us for doing quantum field theory. As we'll see over the next few lectures, this is basically one of our building blocks, quantum field theory. So our plan for the next few lectures is we're going to, tomorrow, we'll introduce interactions. And what we're going to do is we're going to see that scattering amplitudes, so basically an amplitude for some set of initial particles to scatter and then result in some set of final particles, can be related to time-ordered products of fields. So here is our simplest example of a time-ordered product of free fields. So tomorrow we'll see that we can relate these scattering amplitudes to time-ordered products of interacting fields. And then on Friday, what we'll see is that we can relate these time-ordered products of interacting fields into time-ordered products of free fields, which can, even if we have n fields, we can then relate the time-ordered product of n free fields to the time-ordered product of two free fields. So this is our basic building block. And by the end of Friday's lecture, we'll see how to relate the amplitudes that we're interested in, scattering amplitudes in interacting theories, back to this simplest or simple amplitude in a free theory. So that's where we're going. Any questions on that? All right, I'll see you this afternoon, Victoria.